I would like to talk a bit about probability of detection, which is one measure of reliability and safety of the system, and to compare it with other more conventional NDT techniques where you have an operator doing the inspection. So I have been involved in a group of the SAE about probability of detection. So David Petrovsky mentioned, so there are two ARPs the group has been working on. One is the 6461, which is more generic, and then the 6821 that is more centered on probability of detection. So I will give a quick overview of this paper because there has been good progress and good material here, and it's going to be published soon, I understand. So in fact, these pictures come from there. There are different SHM technologies for different materials and different defects, like you have already discussed about PCT with guided waves, carbon nanotube, eddy current arrays, or comparative vacuum monitoring, or strain gauges, and they are at different stages of maturity and are applicable to different structures. They can be used to detect metallic cracks, corrosion, delamination, debonding. So this is the heading of the ARP I mentioned. So the group let me use these slides for the presentation, taking into account that there might be some minor changes. So the objective of this ARP is to quantify the damage detection capability of structural health monitoring systems while considering all factors that may affect SHM performance. So to make sure that the probability of detection takes into account all the sources of variability, the paper has already listed different sources to take into account. So this is taken from the index. So it can be, for example, damage size, damage shape, manufacturing variability, then variability over the life of the aircraft with aging and environmental aspects. This is an important thing that has to be demonstrated. Variability of the equipment, sensor-to-sensor manufacturing variability, cable length, for the installation sensor positioning, and then interrogation conditions, durability factors, human factors, yes. Then one way so the system collects information from the sensors, and then some of the systems give damage indexes, which is a number that is the result of engineering development, and this is often proprietary algorithm. So it gives you a number. So we can see here in this example for a PCT sensor, here you can imagine is a crack growing, and for a certain crack length it gives a damage index, and the system is tuned that above a certain damage index, here in red, it will give a positive that there is a damage. So then in chapter 7, there's statistical methods to evaluate SHM capability. So these are purely statistical and can be applied to any type of damage. So you collect the data that can be your damage indexes or other measure of your damage, and then you introduce it into a statistical analysis. So before, with conventional NDI, there was MIL Handbook 1823A, and this is the next step to take into account SHM technologies. So one of the methods discussed is the 2929, which is a non-parametric method where you assume that you are, for a certain crack length or damage index or damage size, you take different samples and you see the resulting damage index, and if it is green, it we can say it has given you the recognition of a damage, and when it is red, it didn't recognize it. So this technique means that you have 29 samples of that crack size or damage size, and you request that all 29 of them are recognized. So then this is statistically the same as having 90% of the damages recognized with 95% probability. So this is, yes, sampling from a binomial distribution. Here are details that I will not go into, but it gives you for that sample size, what is the probability that your proportion of green lights is high enough, like it has to be 90% or higher 95% of the time. And what happens with statistical sampling is that the more samples, the larger your sample size, the more confidence you have on the results, so the more peaky this distribution will be. Then another method, different from 2929, is so that size of deterioration at detection. So here you can, each of this cloud of points, green, blue, this is one crack that is growing, and you have several measurements. So when it crosses the threshold of detectability, which is the damage index, you mark these black points. So then this is the data that you will use. So you have, this one was discovered at 4 point something, 5, and then this was only detected at about 6 millimeters. So then you will take the crack length, that is the 90-95 probability that will be detected, that will be closer to the larger damages, like 6. I imagine in this case it will be 6 something millimeters. When you use a parametric model, it means that you are assuming a shape of the probability distribution. So then there is the step of hypothesis testing, which is choosing from which probability distribution it came from, and looking for the family of distributions that has the best fit. So in this case, the best fit was a normal distribution. In the right one, it was a log normal. So it can be done visually, or it can be done more scientifically to look at which distribution will have the highest probability to have happened with this particular sample. Then there's the more sophisticated method, which is the random parameter model. So we have the same cloud of points as before, but then the idea is to fit a regression line for each of them. So then before we were only using the data of the crossing, now we are using more points for the regression, and then the method takes into account the variability of the intercepts and slopes of these lines, and calculates, so it makes like the best use of all the available data, but then it's a bit complicated method, and also it's using data points far away from the area of interest. For all these methods, it is recommended to have somebody with solid knowledge of statistics to make sure that the interpretation of data is correct. So it's a Bayesian approach, and here are some details of the analysis. Okay. Finally, so these models are blind about the data. They collect clouds of points and then analyze them probabilistically, but they need a lot of data for this. So then there is another approach which is the model-assisted probability, MAPOD. So it's to improve the effectiveness of POD models with less data. So here you can benefit of knowledge of physics of the problem, So, for example, if you know the effect of some parameter has on the damage detection, then you will implement it in your model. So, what could imagine hypothetically? I don't think it exists yet. Like for PCT, if you know that the effect that the size of your panel has on the detection, then you don't need to test all the sizes. You test a few, and the rest you interpolate by analysis. So you need to do some experimental adjustments with design of experiments, and also some theoretical adjustments taking benefit from your physics. But this is a more complex approach, and this is not so evolved yet, as far as I know. Then I will go in a more wider concept of SHM certification. So this MORPHO is for engines, so this is for aeroplanes, so this is more the area I'm more familiar with. So this is a novel application, so it is about monitoring parts with difficult access. The benefit is you wouldn't have to remove the linings, gullies, so it's a benefit, commercial benefit in operation. But this also removes opportunities to detect damages, because sometimes damages are detected not with the plan inspection, but with some other zonal inspection of the area. So we have to keep a level of safety, like Oscar was saying, equivalent to conventional inspections, but overall taking into account all of the opportunities of detection. Then the applicable regulation, the core regulation is 25571, is that there has to be to show that there will be no catastrophic failure due to fatigue. So some analysis of damage growth is done, and inspections are set in place to show that damage will be detected before it's catastrophic. So what is affected in this case is the detectable crack length. So it's different if an inspector goes and looks, or if there is a sensor. So the probability of detection has to be sufficient for the crack that you think you are going to detect. Then this is about other regulation we have, which is Part M, which is for maintenance organizations. So this is another side of the continued airworthiness. Because then there will be maintenance organizations that have to follow this process and have the sufficient information. So this is the interface between initial and continued airworthiness, and this is the information is traditionally transferred with the ALS, which is the mandatory part of the maintenance manual, and MRBR, which is the part that is continuously monitored and can be escalated. So the question also arises, who will do the data analysis of any findings in service by the system, the TC holder or the maintenance organization? So the TC holder, it's better if they have visibility of what is happening to the whole fleet, but then there are some operator-specific environments, and also it's important to take into account that the CAMOs have sufficient visibility. Some certification challenges are to distinguish between installed versus ground equipment. So we normally certify installed equipment, but here if you are depending on ground equipment, we think it should be reliable and qualified as well. Another challenge is that there are technologies that are very sensitive to specific configurations, so the probability of detection has to be evaluated for all these configurations, for which we will need a test pyramid. And then at a lower level, coupon level, there is the design of experiments with representativeness of parameter combinations. Then this requires quite an effort of companies to develop a sufficient demonstration, the technology has to be mature. So we see that there is a gradual process of even years of doing tests and trying different solutions and process control. We are thinking what should be the equipment qualification standard, what are the necessary calibrations, environmental and durability tests, and then the qualification of inspectors. A very big discussion in the working group was the sample size. So a size of 20 sensor crack pairs is recommended as typical. So if your probabilistic model is correct and you take your sample size into account and your variability into account, this is correct. But then then your sample has to be representative. So if the technology is sensitive to different sources of variability, the number of experiments will have to increase. And also if the technology is sensitive to the geometry and the level of assembly, a test pyramid will have to be developed to the coupon to the assembly level with an understanding between levels, preferably with understanding of the physics. So for number of specimens, as said before, the objective is 1995. The uncertainty decreases with the number of specimens. So if this is the larger your sample size, the more peak your distribution becomes. But then variability is inherent to the design and its implementation. To reduce uncertainty, there should be a robust step-by-step implementation and test pyramid. There should be a process for the test sequence as for NDI. It should increase with the number of configurations tested, with the number of pairs of sensor damage, and there is a trade-off between development and operation cost. The threshold, the red line we saw before, should be established not only to limit the missed damage, so the false negatives, but also to ensure there are not too many false positives, so to not to have complacency as was presented in the presentation before, because this is not only a cost but a safety issue. So if the inspector always says positives that are not true, they lose trust on the system, and this depends on the signal to noise ratio. So then maturity steps we are seeing in terms of risk in operation. So we prefer to see sequential phases of characterization to gain confidence. So first to double check the existing crack with redundant inspections that are well validated, but of course this has no commercial interest. But this is to gain knowledge and to gain maturity. Then to go to SHM only and no cracks allowed. And then the last stage will be the most risky, is SHM only with crack growth monitoring, so what is called flight with known cracks. So the last one is more challenging in terms of risk, but in terms of detection, maybe it's easier to follow a crack, you know where it is, than to put a sensor that waiting for a crack to appear. So for flight with known cracks, this is the last maturity step. Currently, the policy we have for flight with known cracks is that a crack should be repaired except in very exceptional circumstances and with a number of conditions, including ultimate load capability. The policy should be complemented to have awareness. So now we are thinking, in view of SHM, that this policy has to be rethought to take into account the situation where there is a very controlled crack that was discovered very soon because of the good SHM technology. So there is a very long margin for it to become critical. But if we accepted this, it would have to be with very important considerations, that the crack and the load spectrum are very well understood, that there are other opportunities for detection, that the system is capable to identify if the crack changes direction, for example, if it is single or multiple load path, and the residual strength and life. So that was it from my side. Thank you.